Welcome to This Explainer. Today, we are literally building the physics universe from the ground up. We're going to take those complex, sometimes intimidating mathematical equations and translate them directly into the physical actions of our everyday lives.
All right, to kick things off, I want you to picture something for me. Imagine a bungee jumper suspended right in midair, a massive train accelerating down the tracks, and an apple just falling from a tree. Now, ask yourself, what invisible physical laws unite all three of those things? It might sound like a bit of a trick question, but the truth is, the exact same fundamental principles govern every single one of those events.
Here is our roadmap for today. We'll start with the physics of work, move on to the work-energy theorem, and then dive into kinetic and potential energy, elastic energy, conservation of mechanical energy, and we'll wrap the whole thing up with mechanical power.
Let's dive right in with part 1, the physics of work.
Now, I gotta warn you right up front, work in physics, it has a very, very specific meaning compared to how we use it in everyday conversation. In physics, work isn't about sitting at a desk typing out emails all day. Work is literally only done when a force causes a displacement. Mathematically speaking, it's the scalar dot product of the force and displacement vectors. Fundamentally, it's all about energy being transferred to or taken from an object by a force.
Think about it like this. If you apply a force to speed something up, you're increasing its kinetic energy, right? So you perform positive work on it. But on the flip side, if you hit the brakes to decelerate a moving car, you're actively decreasing its kinetic energy. You're extracting energy from the system, which is the exact equivalent of doing negative work. If we strip this down and look at it in just a single dimension, the amount of work you perform really comes down to just two key variables, the applied force and the resulting displacement. Basically, if there's no displacement, there is absolutely zero work done, period. It doesn't matter how hard you push. And look at how the angle between your force and the object's displacement completely changes the game here. Pushing a car forward in the exact direction it's moving, that's an acute angle, so that's positive work. Friction dragging against a sliding block, that's an obtuse angle, making it negative work. But here's the wild part. Think about carrying a really heavy box perfectly horizontally across a room. The upward force you're exerting is at a 90-degree orthogonal angle to your forward movement. And since the cosine of 90 degrees is zero, technically speaking, you are doing zero mechanical work on that load. Crazy, right?
Moving right along to part 2, the work-energy theorem.
Okay, let's connect the dots between the action of work and the actual concept of motion. Watch how neatly this all comes together step by step. If we combine our standard kinematic laws of motion with Newton's second law, force equals mass times acceleration, we get this beautiful derivation. We start with work equals force times displacement. Substitute the force, replace the acceleration, and the whole thing simplifies down to a really neat formula, work equals 1/2 mass times velocity squared. And that is exactly equal to an object's change in kinetic energy. So the net work done on an object literally becomes its motion.
Which brings us to part 3, kinetic and potential energy. So we know that work results in a transfer of energy. But in mechanical systems, this energy usually manifests in two totally distinct ways. First, there's kinetic energy, which, as we just saw, is the active, moving energy of a body. If a train is barreling down the tracks, it possesses kinetic energy. But potential energy is a whole different beast. It is stored energy just waiting to be unleashed. It exists purely because of an object's spatial configuration or its position within a conservative force field. Think of the gravitational potential energy of that apple hanging way up in the tree branches. Because it's raised up against gravity, it stores energy equal to its mass times gravity times its height. And that leads perfectly into part 4, elastic potential energy.
But hey, potential energy isn't just a gravity thing. Remember our bungee jumper from earlier? Hooke's law tells us that the force required to stretch a spring is directly proportional to how much it stretches. So, when you stretch or compress any elastic material, you're actually performing work on it, and that work gets stored as elastic potential energy. It's the exact same principle at play when a trampoline bed stretches downward under your weight, when an archer pulls back a bowstring, or, my personal favorite, even when your very own muscles contract and act like biological springs, storing up energy for a big jump.
Next up, part 5, conservation of mechanical energy.
Now, this is where the physics universe just gets wonderfully elegant. These two forms of energy, kinetic and potential, they are beautifully intertwined. Let's look at a falling ball. In a system where only conservative forces, like gravity, are doing the work, that means we're going to completely ignore non-conservative forces like air resistance for a second. In this scenario, the total mechanical energy is perfectly conserved. The gravitational potential energy that the ball has at the very top is completely, seamlessly converted into kinetic energy as it accelerates downward. What it loses in height, it gains in speed. The total sum of the two never changes.
But hang on a second. Up to this point in our explainer, we've completely ignored the clock, right? I mean, whether you lift a huge box of books up a flight of stairs in 1 single second, or you take a grueling, hour-long climb to do it, the total physical work is mathematically identical. But as anyone who has ever moved apartments knows, the effort feels drastically different.
And that discrepancy brings us to our final section, understanding mechanical power.
Power is what finally introduces time into our equations. It's a physical scalar quantity that measures exactly how fast energy is being transferred from one state to another. It's the rate of doing work. You simply divide the total work done by the time it took to do it.
Now, we can actually look at power through two different lenses. First, over a long, macroscopic period of time, like taking a road trip. That gives us average power, which is just total work divided by the total time interval. But we can also look at instantaneous power. This is the specific amount of power being generated at the exact split second an engine applies force at a certain velocity. If we take the mathematical limit as time approaches zero, instantaneous power equals the force vector dotted with the velocity vector. Oh, and before we wrap up, here's a fun little fact about how we measure all of this. The standard SI unit for power is the watt, which is 1 joule of work per second, named after James Watt, the steam engine pioneer. But when we talk about larger machines like cars, we still use the old-school horsepower. And for the record, exactly 1 traditional horsepower is equal to 746 watts. So, as we finish up this explainer on the building blocks of mechanics, I want to leave you with a bit of a brain teaser to test what we've learned. Imagine you push against a massive, totally stationary concrete wall all day long. You push until you are completely, utterly exhausted, and every drop of your biological energy is spent. Since the wall's displacement is an absolute zero, how much physical work did you actually do on that wall? I'm going to let you ponder that zero displacement equation for a bit. Thanks so much for hanging out with me as we explored the fascinating interplay of work, energy, and power.